move on to differentiation, which is on chapter 3. So first of all, we're going to take a look at the derivative, which is just one of the most important terms in calculus. Derivative and tangent line. So we will try to find the slope of tangent line to a curve at a point. Use the limit definition to find the derivative of a function and try to understand the relationship between differentiability and continuity. So first of all, let's take a look at tangent line problem. And in calculus, we have four major problems that mathematicians are working on during the 17th century. First one is tangent line problem. Second one is velocity and acceleration problem. The third one is the minimum maximum problem. And the last one is the area problem. I'm going to get to each one of them in the later sections. And each problem involves the notion of a limit, which we already learned. And calculus could be introduced with any of the four problems. Okay. So first of all, let's take a look at the tangent line problem. So essentially, the problem of finding the tangent line at a point P comes down to the problem of finding the slope of tangent line at a point P. So anytime we try to find a line, slope is a very important notion. So basically, we approximate the slope using the secant line. So this is our point C. And we find a point which is kind of close to point C, right, with the delta x, right? So the horizontal distance from the point C to the nearby point is delta x. Okay, and the coordinates for this, obviously at this point, this is C plus delta x. That's why it becomes the x-axis for the nearby point, and the f of C plus delta x becomes y coordinate. So in this case, then the slope could be estimated using vertical change over horizontal change. Vertical change becomes f of c plus delta x minus f of c. Vertical change. Horizontal change is c plus delta x minus c. On your denominator, we cancel c here. That's why we end up with the slope of secant line becomes this. Right? Slope of secant line equals fc plus delta x minus fc over delta x. So right hand side of this equation is a difference quotient. The denominator delta x is change in x. The numerator delta y is the change in y, right? Which is f of c plus delta x minus f of c. So that leads us to a definition of tangent line with slope m. So if function f of x is defined on an open interval containing point C, and if the limit for delta y over delta x when delta x approaches 0 equals the limit when delta x approaches 0, for f of c plus delta x minus f of c over delta x, and that's going to be, and this is the slope of the tangent line. Okay. Then the line passing through C, f of C with the slope m is the tangent line to the graph of f at the point C, comma f of C. The slope of tangent line to the graph of f at the point C, comma f of C is also called slope of the graph of f at x equals C. So slope of tangent line equals to limit delta x approaches 0 for f of C plus delta x minus f of C over delta of x. And once C is given, right, given the point, then you'll be able to find the slope of the graph of f of x at that point. So this is the exactly example I want to go over. Find the slope of the graph of f of x equals 2 times x minus 3 at a point 2, 1. If you draw this graph, 2x minus 3, so it's passing through so y-intercept x equals 0, when x equals 0, and y equals -3, so we have the first point 0, -3, second one, when y equals 0, x equals to 1.5, which is 3 over 2, and the point 0, 3 over 2, 0. So we have two intercepts that's graphing, right? X equals 0, that's on the y-axis. -1, -2, -3. Right here. So 1 point is right here. Second point is 3.302. 302 here. Okay. So that's our line. And we basically want to find out the point 2, 1, that's right here. We find the slope at that particular point, right? Slope of tangent line at that particular point. So then we're going to use the slope equal to slope of tangent line equals limit when delta x approaches 0, f of c plus delta x minus f of c over delta x. In this case, c equals to 2. So we have a so this is basically limit delta x approaches 0 for f of 2 plus delta x minus f of 2 over delta x. Okay, so f of 2 plus delta x is basically 2 times 2 plus delta x minus 3 minus f of 2, which is 2 times 2 minus 3 over delta of x. When you expand, you get 4 plus 2 delta x minus 3 and minus 1. So eventually we end up with a cancel 4 minus 3 minus 1 becomes 0. So we have limit delta x approaches 0 of 2 delta x over delta x. And that becomes 2. Cancel delta x becomes 2. And the limit of a constant is a constant, right? So the slope of tangent line at this point 2, 1 . is equal to 2. Okay, so that's a detailed solution. You can take a look at the PowerPoint, has a more detailed like solutions if that helps. Okay. So slope function at 2, 1 is equal to 2. So definition of the tangent line to a curve does not cover the possibility of a vertical tangent line. For vertical tangent lines, you can use the following definition. If f is continuous at c, and limit for when delta x approaches 0 for f of c plus delta x minus f of c over delta x equals infinity. This is positive infinity. Or limit when delta x approaches 0 for function f of c plus delta x minus f of c over delta x equals to negative infinity. Then at the points c, comma f of c, we have vertical tangent line. Okay, so either one of these is satisfied, then we have a vertical tangent line. So let's take a look at the example, right? For the function shown below has a vertical tangent line at c, f of c. So this is a typical vertical tangent line. Basically, it's just vertical line, right? But it's a tangent towards that point. So the graph of ff is vertical tangent line at c, f of c. So if the domain of f is a closed interval, square brackets a comma b square brackets, you can extend the definition of the vertical tangent line to include the endpoints by considering continuity and limits from the right, x equals to a, on the left endpoint. On the right endpoint. So you consider continuity and limits from the right for x equals a and from the left for x equals b. So let's take a look at the definition of derivative of a function. The limit used to define the slope of tangent line is also used to define one of the two fundamental operations of calculus, differentiation. A definition of the derivative of function. The derivative of f at x is given by it's defined by limit, right? F prime of x. This prime of x represents the derivative of f of x. So f prime of x equals to limit when delta x approaches 0 for function f parenthesis x plus delta x parenthesis minus f of x over delta of x. Provided the limit exists for all x for which the limit exists, f prime is a function, f prime of x is a function of x. Okay. So this is a limit definition of the derivative. That's a limit definition of derivative. And we're going to use this definition to find the derivative. The process of finding the derivative of function is called differentiation. Okay, so differentiation is a process to find the derivative. A function is differentiable at x if its derivative exists at x and it's differentiable on an open interval, parenthesis a comma b, if it is differentiable at every point in the interval. Yeah, addition to f prime of x, people also use, they all equal, right? This is equal to that, equal to that, equal to that. People also use dy over dx. Also, you see people using y prime. You may also see d over dx square bracket f of x square bracket. Also, this is d, capital letter D, subscript x square bracket y square bracket. They are all notations for derivatives, right? And they are equivalent. But the most common ones would probably be the first three. This one, this one, this one, this one, this one. 5 different ways of writing derivative. The notion dy over dx is read as derivative of y with respect to x. Simply dy comma dx. Using limit definition, you can write it as dy over dx equals to limit delta x approaches 0 for delta y over delta x. Delta y equals to f of x plus delta x minus f of x over delta x. That's why it's a prime of x. So there's different ways of writing derivative, but just make sure you know they are equivalent to each other. So let's learn how to find the derivative of f of x equals to x cubed plus 2x. So we're going to use the limit definition. So the prime of x equals limit when delta x approaches 0 for f of x plus delta x minus f of x over delta of x. So we're gonna just use the limit, the function notation f of x plus delta x equals to x plus delta x cube plus 2 times x plus delta x, right? Basically just replace this x plus delta x into x. That's why we have that. Okay, limit delta x approaches 0. So we're gonna expand this. It becomes x cubed plus 3x squared times delta x plus 3x times delta x squared plus delta x to the third plus 2x plus delta x, and f of x is x cubed, so minus x cubed plus 2x, right? So that's your complete numerator, and the denominator basically just delta x. So let's simplify that as x cubed get cancelled. Let's expand it, x cubed plus 3x squared times delta x times 3x plus 3x times delta x squared plus delta x to the third plus 2x plus 2 times delta x minus x cubed minus 2x over delta of x. So now we cancel x cubed, we cancel 2x, so everything else remains, right? Let's see what remains. 3x squared times delta x plus 3x times delta x squared plus delta x to the third plus 2 delta x divided by delta of x. So every single term has a delta x, so if you factor out that, everything gets cancelled. Okay, so we end up with divide into each one of them. Becomes 3x squared plus 3x times delta x plus delta x squared plus 2. So now when delta x approaches 0, we replace delta x with 0. Replace delta x with 0. So we end up with limit delta x approaches 0, 3x squared plus 0 plus 0 plus 2. So limit delta x approaches 0, 3x plus 2. And with respect to delta x, x is a constant, right? So for any constant, the answer is 3x squared plus 2, right? So the derivative of f of x equals x cubed plus 2x is basically 3x squared plus 2. So this is detailed solutions to the problem we just went over. And next, let's take a look at the definition of differentiability and continuity. Differentiability meaning it's differentiable everywhere. And continuity means continuous. Okay, so the following alternative limit form of the derivative is useful in finding a relationship between the differentiability and continuity. The derivative of f at c is f prime of c equals the limit when x approaches c. Numerator is f of x minus f of c over denominator of x minus c. And this is what they call alternative form of a derivative. Providing a limit exists, right? That always is an assumption. So when as x approaches c, the secant line approaches the tangent line. Okay, so it's meaning this point getting infinitely close to this point. Then eventually the secant line becomes tangent line, moving towards that. Okay. So if, as you can see from the graph, right, slope of secant line. In this case, this is the delta of y. This is delta of x. Okay, delta of y equals f of x over f of c. F of x over f of c minus f of c, and delta of x is just x minus c, right? That's why we have that. So basically, just pretty similar to the other definition, but with a different different concentration. Note that the existence of limit in this alternative form requires that one-sided limit when x approaches c from the left. C minus left. This is right. Exist and are equal. Okay, so limit x approaches c minus for f of x minus f of c. X minus c must equal to limit when x approaches c from the right. These one-sided limits are called derivatives from the left and from the right, respectively. It follows that f is differentiable on a closed interval a square brackets a comma b square brackets if it is differentiable on ab, and if the derivative from the right of a, the derivative from the left of the b both exist. If a function is not continuous at x equals c, it is also not differentiable at x equals c. So, no, not continuous, not differentiable. Indicates not differentiable. For instance, the greatest integer function is not continuous at x equals 0. So it's not differentiable at x equals 0. Okay. The function f of x equals the absolute value of x minus 2, shown in figure 2.12 below. It's continued at x equals 2. Right, it's continuous everywhere actually. However, it's not differentiable because the derivative from the left and derivative from the right are not equal to each other. So limit when x approaches 2 from the left for f of x plus for function f of x. Okay, so erase this for function f of x. Approaches 2 from left, so this value must be let's use the definition of the derivative from this 2 from left. So in this case, limit x approach 2. So this thing is negative, so we're going to put negative x minus 2 minus f of 2, f2 0, right? Over x minus 2. As you can see, we just end up with a limit x approach 2 from left. It's negative x minus 2 over x minus 2. When we cancel that, it becomes negative 1. So the derivative from the left is actually negative 1. And let's take a look at the derivative from the right. Right limit when x approaches 2 on the right, f of x minus f of 2 over x minus 2. In this case, f of x now is from the right hand side, so this value is always positive. So we have a limit x approaches 2 plus x minus 2 minus f of 2, which is 2 minus 2 over x minus 2. And this thing get cancelled, becomes 0. We got limit x approaches 2 plus x minus 2 over x minus 2. We cancel that and end up with 1. So from the right, you can the derivative is 1. Okay, so the derivative from the left is not equal to the derivative from the right, so it's not differentiable then. So this is basically detailed solutions. They're not equal, so derivative does not exist. F is not differentiable at x equals 2. And the graph of f does not have a tangent line at a point 2, 0. At this point, no tangent line. Okay, differentiability implies continuity. That's what we learned from the previous example. So if f of x is differentiable at x equals c, then f of x is is the continuous at x equals c. So differentiability implies continuity, not the other way around, right? If function is continuous, it may not be differentiable. So the following statement summarizes the relationship between the continuity and differentiability. If a function f is differentiable at x equals c, then it's continuous at x equals c. So differentiability implies continuity. The second one, it is possible for function to be continuous at x equals c and not be differentiable at x equals c. So continuity does not imply differentiability. This is exactly, it's continuous everywhere, right? But it's not differentiable at x equals 2. So differentiability implies continuity.